Start. Okay. Right. Let's revise our understanding of an atom. Okay. Notice something very quickly. Let me just. Okay. Let's revise our understanding of an atom. So, for an atom structure, okay, for an atom structure, like for example, this, okay, what we understand is in the middle of the nucleus, we have a very tiny nucleus comparison to the electrons. Okay, um, so we have atoms in the middle. What am I talking about? Suddenly haywire again. Okay, we have our nucleus in the middle here. Then in the nucleus, we will have protons plus neutrons. And then we have the electrons orbiting around. Okay, this is just a simple example because from your concept of chemistry, electrons should be 268 or something like that. Okay, so over here, electricity basic is on atom as well because okay, because proton is a positive charged particle. Okay, the mass of a proton is 1.673 times 10 to the power of negative 27 kg. Neutron is no charge, is neutral, and the mass is actually 1.675 times 10 to the power of negative 27 kg. Electrons is negatively charged with a mass of 9.11, two decimal places in SPM, times 10 to the power of negative 31 kg. So in an atom, all right, in an atom, usually the charges of electrons and protons are equal in magnitude. Okay, means if there is two protons, then there will be corresponding two electrons in the atom. So this comparison, okay, if the atom size, the whole entire atom size in comparison lah, okay, the nucleus, if comparison of the whole atom size is a few kilometers wide, okay, let's just say roughly around 5 kilometers wide, for example. The nucleus, which has the highest density of the mass of the atom, it's situated in the center, and the atom would actually be the size of a basketball only. Okay, so that's how wide and how far range electrons to the nucleus itself. So, but in actual situation, right, in actual situation, the size from the radius of the nucleus towards the outermost electrons is around 10 to the power of negative 10 meter. Okay, to us it's very small, but to electrons, that range is very, very big. Okay, so that is what atom is: protons, neutrons, and electron. Okay, so in chemistry also we learned about positively charged elements or positive ions and negative ions. Okay, so also refreshing memory on that. For example, neutral lithium atom. Okay, how do we consider it as neutral lithium atom? We have 1, 2, 3 protons in the nucleus, 4 neutrons. But then in order to consider it as positive or negative depending on the number of protons and electrons. So here there is 3 proton and 1, 2, 3, 3 electrons in lithium. So 3 positive charge, okay, 3 positive charge and 3 negative charge electrons. So positive plus with a negative 3, it will be number of electrons equals to number of protons, therefore zero net charge. And that is the reason why this picture of lithium is a neutral element. Now, how do we consider it as positively charged? In chemistry, positively charged means less electron. Okay, so here you would see that in the nucleus itself, there's 3 protons and then 4 neutrons, but electrons right now is 2 electrons. Probably the third electron has been shared outside. Okay, so there are fewer numbers of electrons compared to protons. Positive 3 plus negative 2, you get positive 1. So that's a positive net charge. That's the reason why this lithium ion is considered as positively charged. Okay, so lastly, how do we change lithium to become negative? You have 3 protons, still the same, 4 neutrons. When we talk about electricity, we are not going to change the nucleus. All right, changing the nucleus to identity, that is only happening in nuclear physics. So for electricity, we won't consider about changing the nucleus because it's very difficult to remove it at a natural situation. Okay, so over here, the electrons right now, instead of 3 as the neutral, it has an additional electrons that is being shared by other atoms in. So the electrons now have 4 electrons in this atom. So that's positive 3 protons, negative 4 electrons. So there's more number of electrons compared to protons. Therefore, this is a negative net charge. All right, negative lithium ion. So when we talk about positive charge and negative charge in physics, in electricity, we are actually talking about the atom being a lack of an electron, right? It's the atom that is lack of electron, then it is positively charged, right? It's a positive particle. It's a positive charge particle. If the electrons is more than the proton in that atom, that that atom becomes negatively charged. So in electricity, we consider that negatively charged atom to be a negative element, right? Negative charge in electricity. Because previously, when you learn in science, you learn that electricity is a positive charge and a negative charge. But it's still, the basic is still coming from atom. If it has more protons than electrons, it's a positive charge. If it has more electrons, okay, if it has more electrons compared to proton, then it is a negative charge particle. So that is where positive charge and negative charge comes from. So again, one thing that we notice that physics still goes back to atoms. All right. So in electricity here, all right, we first talk about electric field. Okay. Electric field is an example whereby, okay, electric field is a region where an electric charge experience a force. Okay. When you learn gravitational, we did mention about Newton's universal law of gravitational, whereby when two object has mass, they will have attractive force, right? They have gravitational force. So atoms and atoms have mass. When atoms and atoms have mass, they will have a force. Okay, that force, you won't learn it in SPM. All you just need to know is there will be a force between them. So this force, okay, let me open up my simulation. Okay, we are talking about electric field right now. Electric field is a region. Okay, electric field region, for example, here. This is a positive charge particle. All right, which means that there are 5 additional protons compared to the electrons in the atom. So it is a positively charged particle. Okay. If you guys have any question, as usual, write down, send me the message in the chat box. Okay, so here, a positively charged particle, the arrows that you are seeing over here are all electric field lines. Okay, these are all electric field lines. As you notice, the further away, right, the distance further away means that it's much more weaker. When it's closer together, it is much more stronger. Okay, so electric field lines is when I have, let's get a test charge. Okay, if this, all right, if you see there's a dot moving around on the right hand side corner of this part, okay, that's a test charge. Test charge, we assume it as a positive charge, but the nature, whether is it positive or negative, it doesn't matter. So when I put this test charge here, you will notice that it is being pushed away. So when a test charge is placed on the electric field, it will experience a force. All right, that force will either be pulling it or pushing it away. Okay, so let's just say, for example, this is positively charged. Now I'm going to change it to negatively charged. Just now, when it's positive 5, I put a test charge here. The electric field lines of positive is moving outwards. Right, positive charge, the electric field lines is moving outwards. It's like a person who has positive personality. the person will obviously be happy, very excited. So that happiness and excitedness will easily influence people outside, and it will cause people to be more and more happy. All right, I'm talking about happy people influencing happy. Yeah. So, but if I were to put a test charge at this position, okay, the happiness of that person will actually be spreading out. So for a positive charge, the middle +5, when I put another neutral test charge here, it will actually push the test charge further away along the electric field lines, because positive charges, the electric field lines is going out. But if I change that atom to be negatively charged, which means it has 5 extra electrons compared to proton. All right, so it's negatively charged, and do you notice now the electric field lines is moving into the atom, all right, into that charge itself. So when it moves into a charge, into that -5 charge, I take a test charge, I put it over here. Okay, look at what happened to the test charge. That test charge now is moving towards the -5 charge. Okay, and you would notice also one thing: when it gets closer, let me show it you again. When it gets closer towards the -5, it will move faster. Reason why it move faster is because the force is already getting stronger. But if I change this to +5, all right, it will move away. Look at how fast it move away when it's at closer towards the +5. Okay, so this is showing electric field lines to all of you. Okay, so again, electric field is a region where an electric charge will experience a force. That force could either be repulsive force, and it could also be attractive force. Okay, it depends on the charge, all right, of that particular electric charge. Okay, if it's more proton compared to electron, it's positive charge. If the atoms has more electrons compared to proton, then it's negatively charged. Okay, these are a few simulations that I used previously. Now, we need to learn how to sketch electric field based on your syllabus. Okay, so these are a few indication of what we need to understand. The number of lines are directly proportionate to its magnitude. Okay, so I'm going to show you this at the side. Okay, look at +5. The minute when the statement here is number of lines, number of electric field lines are directly proportionate to the magnitude. Stronger field, the lines are closer together and they are more. Weaker fields, the lines are further apart. So if you look into this simulation, okay, when it's further away at this region, the electric field lines are further away from each other, means that this region, the electric field or the force is actually weaker. But as it gets closer towards the charge, all right, as it gets closer towards the positive charge, the distance between the electric field lines are actually closer, means the electric field are stronger there. And then the magnitude of the charge will be represented. Okay, the more lines, the more number of lines, right? The number of lines represent the magnitude. Okay, sometimes there's no specific value. In SPM, we draw at least 5 lines or 6 lines coming out. Okay, later I will show it to you guys. So here, +1, there's 4 lines. When +2, it becomes 8. When it's +3, it becomes 12. Okay, so it increases, the number of electric field line increases. And one thing you would notice that all this line will not touch each other, it will not intercept each other. Okay, even when there are 2 charges next to each other, the lines will not touch each other at all. Okay, it cannot touch each other at all. So electric field lines, number of lines are directly proportional to its magnitude, but thankfully SPM, we only considered it as the same charges. All right, the magnitude is the same. Lines cannot intersect, it cannot touch each other, it cannot even pass by next to each other. There must be a space between them. So the arrows, right, the direction of the electric field is positive charge, the electric field is moving out. Negative charge, it is moving inwards. Okay, so that is how we sketch a electric field. And the lines must be from or out of all direction. Okay, all direction in a short while, again, I will mention to you how does it look like. So these lines does not intersect with each other, and the number of lines determine the strength of the electric field. Capital E is what we use to symbolize electric field strength. All right. Capital E is what we use to symbolize electric field strength. So electric field strength is large when, that means bigger, stronger, when the field lines are closer together, and the electric field strength is smaller, weaker when it is far apart from each other. So a positive and a negative charge can produce electric field. One thing is when we look at this particular simulation, electric field lines can stand on its own. Meaning means that even without, this is a positive charge, even without a negative charge, electric field lines can appear on its own. All right, it's independent of other people or other charges. So if it's a negatively charged, also it can stand on its own. Why do I mention this? Because if you were to recall regarding magnetic field, all right, when you recall regarding magnetic field lines is moving from north towards south. When you break a magnet, it will still appear north and south pole on the broken magnet. Okay, so for electric field can stand alone. Okay, they can produce electric field by itself. It doesn't need a partner to produce the electric field. So the below patterns are some of the electric field lines from different types of charges and its location with each other. Okay, so a positive charge, right? Positive charge, we draw the electric field lines. Please do make it a habit. Okay, draw from the atom, all right, draw from the positive charge itself, touching the charge, moving outwards. Do not draw this way. Okay, do not draw whereby this is positive and then your electric field is like this, hanging. I know the textbook sometimes it is like that, but the actual situation, it should be touching. This is wrong. Okay, drawing like this is wrong. You need to make sure that the arrow touches the atom itself. Yeah, I'm a little bit sensitive and particular regarding this because later on you will learn that if it's hanging, then it's going to be wrong lah. Okay, so might as well learn the correct method in the very first place. Now, just now, what I mentioned from the previous slide is that the direction of electric field strength for a positive charge is outwards. It is all pointing outwards. You need to draw the arrow, all right? Like the ray diagram, the arrow matters. So the charge, all right, the charge goes out in all direction. So when you draw an electric field line for a positive charge, okay, you cannot just draw like that. All on the right-hand side. Left-hand side hilang. If left-hand side hilang, sorry to say, this is also wrong. Okay, so if you want to draw an electric field line, it must be all direction. It cannot overlap or it cannot touch each other. Okay, so other electric field patterns, put a remark at your textbook, or if you printed out this particular slide, make sure that you put a highlight here because you need to learn how to draw these electric field lines. So when there's a positive charge particle and a negative charge particle, we assume that they have the same magnitude. The number of lines coming out from the positive should be equals to the number of lines entering the negative. Okay, so here you would see that all the lines does not overlap each other. The closer it is, they will curve a little bit. Okay, this line actually can go here. This one goes further away here, but the top part you don't really have to draw lah. What we concern of is number one, we concern that arrow direction is correct. coming out from positive entering negative. We concern whether the number of electric field lines coming out from positive, is it the same number of electric field lines entering the negative? If it's both charges. Okay, so this is for unlike charges. The electric field lines will out from positive into the negative. If both of the charges are the same, either negative and negative or positive and positive, it will be this, all right? If it's negative and negative, electric field lines entering, okay? But the middle part here, this is a neutral region, okay? At the middle part here, you should not draw any arrows at all because this is where the repulsive force happened. All right, because we know same charges repel each other. So this neutral region is the one that causes the two electrons, the two negative charge or the two positive charge to move away from each other. Okay, so you make sure the middle part, you don't draw any arrows in there. Okay, next is positive charge, and this is a negative charge plate. Now, when we are dealing with a plate, all right, an electric plate, okay, electric plate, the field lines entering must all be equal distance. Okay, the arrows entering the charge plates must be equal distance, especially in the middle part. So, should the number of lines coming out from the positive go into the negative the same? Not necessarily already. That only applies for positive and negative charge. If it's a charge and a plate like this situation, we don't bother already. All we look at is the positive charge. It has to have arrows coming out from all direction. And then for the negative plate, negative charge plate, the arrows going in must be equal distance. Okay, I hope until here you guys are all right. Then finally, the last one is two plates with unlike charges. Two plates with unlike charges from positive, the arrow will move towards the negative. Whatever that is in the middle, the distance are all equal distance. Okay, the distance between the electric field lines in the middle are equal distance. Only the side is curved and it can be slightly further away. All right, only at the side it is curved and it can be slightly further away. Okay, so here, okay, I think the next page is drawing. Okay, maybe let's just do a simple exercises since there is not many people here. Can you enter the class point? Okay, try to enter the class point. I'm not specific about the class name or whatever. Just try to enter class point because I want to see whether your drawing is correct or wrong. Okay, so those who's just listening in and you're unavailable to have your paper and pen with you, maybe you just listen lah, but make sure you observe and understand later on. Because I see not many people, so I think we can just use class point and then I can help you guys to identify which is right and which is wrong. Wan Leong's assistant. Hi, Daryl Tan. $15, $25. Anyone else coming in? Okay. No worries about it. Okay, so I'm gonna close this one. Why this one not working? So long never use class point already. Wait, let me find out where's my class point pergi. This is what happens when I too long don't use. Okay. Alright. Are you able to get it now? I think should be able to draw already. You all try to got any problem drawing or not? Can you all put it in the chat box? Are you able to open the class point and to start drawing? Not
Cannot,
yet.
teacher. Cannot draw.
Okay, wait, let me close this. Just let me close this and open this back. Okay, better. So whoever's is trying to do the picture, try to do it, and then once you get it, then send it in. We'll discuss one or two examples, one or two pictures that you sent in. Anyone doing? I have 4 answers ready.
Teacher.
Yep.
Yeah, the third one's supposed to be upside down.
The one's supposed to be upside down.
Yeah, my bad. My bad.
How are you gonna explain to your SPM examiner?
That's a good point.
Alright, I'm gonna close the submission for the moment. Alright, I just need a few. Okay. Now. Okay, so let's start with my assistant lah, huh? Okay, so over here, recall number 1. Mana my mouse pergi? Okay. Recalling number 1, positive is supposed to be going out. And then negative is supposed to be entering. For those of you who just entered and joined our class, just a quick recap. Positive charge in electricity that you've learned from science is whereby the atom has a nucleus whereby there's protons and neutrons and then the electrons orbiting out. A positive charge in electricity is whereby the number of protons is more than the number of electrons, which means in chemistry we call it it's a negative ion. In physics we call it, more protons compared to electrons. In chemistry we call it as a positive ion. In physics we call it as a positive charge. It's the same thing, but because we are doing different stuff on the atom, so one is called a charge, the other one's called a positive ion. So a negative charge in physics is whereby the number of electrons is more than the proton number. In chemistry, why positive, negative? In chemistry, this is a negative ion. In physics, this is a negative charge. So when we look at the negative here, it is an atom whose electron is more than the proton number. Okay, when we see a positive charge, this is the atom whereby the proton number is more than the electron number. So for those of you who joined us, this is what it meant by the positive and the negative. Okay, now I'm going to erase this off. Okay, let's check what my assistant do, betul or salah. The first thing that I noticed, my dear assistant, ini sudah salah. Entering, coming out from positive, going to the negative, I noticed the number of lines is all tally, but only thing is this one, lor. Okay, this one's sesat a bit. Then here, okay, coming out from positive, going into negative. But remember, what I mentioned just now is if it is within the center part of a positive plate, the distance between the electric field lines are supposed to be equal distance, even though it's coming from a round positive charge. All right. As long as it is entering a plate, all right, it should be equal distance. And the curved part should be at the top. So here should be going in like this. This should be going in like this. And then curve going in like this. Okay. So Daryl Tan, please take note. For this one, all this, I can see that it's quite equally charged. I don't have to measure that. Then I would consider this one as correct. Okay, next. Okay, Putri. Putri's one, a lot of arrows. Takut I tak nampak. But memang the arrows are all correct. Okay, I can see all the direction is going in correctly, coming out correctly. Okay, for this one, okay, again, please make sure it's equally distance. All right, how do you make it equal distance? For me, right, normally I would put my ruler here, and then I would just put a scale there, maybe 0.5 or a few millimeters. I put how to say, the segments over there, so that whenever I draw out, I will come here. Okay, so that was how I used to do it last time. Okay. All right. So the rest of you also please do take note on this. That's how I do it. I measure it first. Okay. Then only I draw the arrows out. Okay. Then here again, Putri, because use a ruler, please. Okay. When you draw, if possible, please kindly use a ruler. So this one is not supposed to be curved. So this picture, this is wrong. Because it is coming out from a positive plate going to a negative plate, it should be equal distance and it must move at the same line. Okay, let's see if I have, this is charge. What I have are all, okay, maybe you can see like this. All right. You see, it is all equal distance. It is all a straight line in the middle of two charge plate. Okay, so please do take note about this. It shouldn't curve in the middle of two plates, two charge plates. It should be a straight line towards it. The only part that can curve is at this corner, curve to the other corner. That's the only one that can curve in a charge plate. Okay, so Putri, take note. The rest of you also check by your own working. So Jairash is obviously using a handphone to draw this.
It's a mouse.
Mouse, okay. All right, so here have to be very careful. That's why I select picture for you to upload image. Okay, so here how am I going to evaluate this in exam? If in exam honestly, if in exam this is going to be like that, baby. Okay, the arrows are correct. All right, the direction of the arrows are correct, but the way that is being drawn, the arrows, that one is a bit concerning. Okay, so yeah lah. Okay, Jarash, take note lah, huh?
Yep.
Okay, for Jonathan, same thing as Jairaj. Very obvious you're using the mouse also. So direction wise is correct. Over here, Jonathan is trying his best to draw it equal distance. So okay. Yeah lah, next time if I select image upload, then use the paper and pencil lah, huh? Okay. All right. Now is Damia. Okay, let's see. This one, good. All right. Then here, okay, she try her very best to be equal distance. Okay, but you see, sekali nampak, I know that this is small and this is big. Okay, Damia's trying her best. So as I mentioned, use the ruler. Okay, draw segments of probably difference of 2 millimeters or 3 millimeters depending on the question. And then the other side also use the ruler to make sure that you get it equal distance and then you draw the line. Okay, Damia? So here positive and then negative. All right, try to be very careful over here. All right, this is like as though that is touching already. So try to be very careful so that it doesn't overlap. All right, but just try lah, okay? All right, we're gonna try another one. Okay, try to use a picture Try use paper and pen to draw it. If it's a straight line, I already mentioned what to do. Okay? Pasal tiba-tiba dia tak nak lagi. Okay. Is it working at your side? This card. Every single time I have to do that. Okay. Try this now. We'll wait for like another 2 more examples before I stop the submission. Whoever that managed to sign in, then I'll just discuss that.
Yeah, 1 minute, Acha. Give me a
Hmm?
minute.
Closing ah.
Sure, wait.
Anyone else want to sign in before I close? 5, 4, 3, 2, 1. All right. Okay, so let's close this. All right, so for Damia, okay, when we have, I'm just gonna draw here first lah. Okay, for my mind. Okay, yeah, if you want to send to WhatsApp and for me to check, then you can send it to WhatsApp. I'll try to put it in. Okay, so I'm gonna show you my answers first for the rest of you. Okay, I'll try to draw as properly as I can. Now, for this is a negatively charged, so normally what I do is I'm using freehand also since I'm using a drawing pad without an line, so I'll try to be as accurate as possible. Okay, so my normal habit is to draw the lines first. Same thing here. Okay, then I'll draw the arrows in. Because this is two negatively charged particle, so what happens in the center is, watch here, what happens in the center is from here, I move in here, and then from somewhere almost the same distance from here, I move in here. Then gap a little bit, move in the other side, gap a little bit, move in here. Okay, I tak puas hati dengan last one. Okay, so that is going to be how I draw it last. So at least there's a very obvious range in the middle here. Okay, then if it's positive, so I'm going to try to draw the equals distance here. So what I do is from here, try to make it as straight as possible that I can. Have to be very careful. Now, the negative charge here doesn't have to be equal distance, but the one that comes out from the positive should be equal distance. Okay, when it comes to my drawing of physics stuff, sometimes I'm a little bit perfectionist on this. Be very, very careful not to touch the lines. Okay, so with that, then I draw the negative in, negative in, negative in. Okay, so that is how I can try to draw lah. For the first question, if I make all the electric field lines curve also can, right? Because textbook also curve since there is repulsion force. Textbook also curve since there's repulsion force. Wait first, Daryl, later I'll get back to you on that question. Okay, so this positive line, because it's positive and positive, same thing you can draw like this as well. Okay, draw the lines. They have the same magnitude because it's positive. All right, the lines should be almost the same as the negative one. It's just that the arrow is going out. Okay, then you just draw the arrow outwards. Okay, so this is how I'm supposed to draw it. Okay, so let's track through the working first, then only I'll get back to your question, Daryl. So the rest of you, this is actually how I do my working. So if you want to screenshot that, you better screenshot that fast. I'm going to go to next. Okay, so here, right, Damia, your we assume that this two positive charge is not far away from each other. So having like this, right, your distance is quite far already. Okay, so it would be better if you can put another lines like this. All right, making it come out. Okay, because the distance between the two charge that you are drawing is actually, it looks quite far away from each other. So the neutral region, the repulsive force region, is not so far away. And when I mention the neutral region and the repulsive force region in SPM, this one no need to mention now, okay? Only for your understanding itself. Okay, but arrow wise, correct. And then here also, the arrows for this one is wrong. The arrows is supposed to come out from the positive, entering negative. Okay, positive people will try to spread their happiness. Negative people will normally keep their feelings inside themselves. Okay, so that's how I remember. Positive go out, negative goes in. Confused. And then Damia, if you notice, your left hand side is all going out, and then your right hand side going into the negative. Okay, be careful with that. Now, Lester. Okay, Lester again. Lester, I ikut hati want to count my the lines. So 2, 4, 6, 8, 9. 2, 4, 6, 8. That's why you have 9 lines here, but you have 2, 4, 6, 8 lines here. 2, 4, 6, 7 lines here. All right. So by right, the number of lines should tally. Okay. So draw a line here, draw another one here, and then add another one here. Okay, so tally it because it looks like it's very far apart from my point of view lah. Okay, so positive charges, all right, from coming out from positive charges is correct, but try to draw field lines at this direction as well. Okay, Lester, add on over there. Don't let this part be empty. And then here also, it shouldn't curve this way. It should curve like this. Because it's positive charge, it comes out and then it curves upwards, not like this. Because like this means that it's as though going towards the other side, which is wrong. This is a positive charge here, so it is actually curving this direction. Okay? Now, again, back to my assistant. Negative line. Okay, number of lines correct. So this one okay. Here, coming out from positive, entering negative. Sudah belajar all the lines arrow betul. Okay, finally. Okay, this one is clear. I think remember someone. Okay, Ting Han's one. Ting Han one very obvious using mouse also. So 2, 4, 6, 2, 4, 6. Okay. Number of lines. Okay, but Ting Han, try to in actual drawing, please make sure that your arrow is proper a bit. I'm trying to see whether is it going out or going in. Okay. All right. But anyhow, so far, okay. This one looks weird. This one looks weird. Positive line go out. Positive people spread happiness. Negative people keep the feeling to themselves. Remember that statement. Positive people spread out the happiness. Negative people keep the feeling to themselves. So positive charge spread out the electric field lines. Negative charge enter electric field lines. So this is a positive and positive thing, Han. So it's supposed to, the arrow is terbalik already. Okay, Teng Han, please take note. Here again at so Teng Han, I'm gonna do some editing onto your diagram. You edit at your own notes. The arrow should go out. Okay. This one, put line here. Going outwards. Alright, Teng Han, please change that for yours, sir. Okay, Hans. Is it any possible method so that I don't have to turn my neck sampai macam ni? Okay. Alright. Daryl, can you, while using Hans working, can you please identify which one you're talking about? Or? Okay, this one positive, enter negative, okay. Positive entering negative, okay. But here also, by right, supposed to have lines over here also lah, okay. Alright, but drawing wise is correct. Positive to negative, correct. Negative, enter, correct. Positive to negative, okay. Positive to positive, okay. So Hans working so far is correct. Okay. Vinaya's, again, I need to turn this. Okay. Negative entering. Good. Vinaya, please do again. Maybe because it's my picture, so it's needs to be closer. Alright, this middle part, don't make it too far away from each other. Alright, the middle part, don't make it too far away. Again, this part, don't make it empty. Okay, so just now, I think Hans also did this mistake. Don't leave this two part empty. Alright, make sure there are lines coming here, going in as well. Same thing over here.
Sure, if we make sure like that, how do we make sure it doesn't like intersect?
So it is better that you draw from here first. Over here, you can draw it closer to each other. For example, this is my lines, and then here, this is positive. Okay, so I get the equal distance first. Maybe you don't want to make the equal distance so close to each other. My disturbance are coming back home already. So here, over here at the positive charge, it can get closer towards each other as long as it doesn't touch. I think you can hear their voice already. All right, so you can draw it like this. All right, then only you draw the remaining ones.
Okay, sure, understood.
Yes, yes. Sorry, yeah. My biggest challenge this week. Okay, so Lishan's one. Okay, so far for me, okay, maybe again as usual, I see it quite far away. So yeah. And then Lishan here also. The other side, don't leave it empty. Alright, here should be okay also. I think it's probably because when you take picture, it took quite close. So for me, that distance is quite far away from each other. Alright, negative signs all moving in. Okay, this one from positive again. Jairaj, here. Make sure they are entering as well.
Okay, sir.
Okay, positive. Alright, good so far. Okay, let's see. I know someone sent me message. Okay, so for I think Vitrika's one, your one also okay so far. And then Harshini's one. Okay, I need to Harshini, I borrow your picture, okay? Let me very quickly. Okay. Borrow your picture for us to discuss. Okay. So Harshini's one. Okay. Just discussion for everyone also. So Harshini's one, sorry to say you wouldn't be getting any marks for your diagram because this negative sign, you should let it touch the charge. Okay, you should let it touch the charges. Okay, so here you have to let it touch. And then the shape of a negative to negative charge is supposed to be like this. Okay, here also. So you draw the charges quite far away. This is very obvious, it's far away already. All right, so you have to make it closer, make sure the line touches the charges, not hanging like this. So this hanging part is actually wrong. Here also, these are both positive charges. So for both positive charges, it's not supposed to curve like this. This is wrong. It's supposed to curve out like this. All right, this curving outwards. Okay, at the center part. Okay, so for here again, make sure that it touches. Don't let it hang. Okay, here also, let it continue to touch it. Okay, like this. All right, Harshini, so please be aware about this. Okay, so drawing part, I think should be okay already. So I'm going to proceed on. Okay, because I haven't even reached half of my slide. Okay, now, so electric field strength. Just now we were talking about electric field. So right now we're going to go into electric field strength. Electric field strength is whereby at a given point at any electric field is defined as the electric force acting on a unit positive charge placed at that point. This definition is from your textbook. So I'm sure you guys have a big, huge question mark. What does electric field uh, charge actually, the strength means? Okay, now. So electric field strength is whereby if I put a positive charge here, all right, I put a positive charge here, okay, and I take a positive charge. This sensor normally test charge and the sensor are positive charge. Another positive particle, all right, another positive charge particle, and I put it over here. This charge will feel as though that it is being pushed away. Okay, if you recall the definition, the electric force acting on a unit positive charge placed at that point. So this main charge is positively charged. So the electric field lines are all going out. Okay, when it's going out, another positive charge is placed at that electric field. It can feel the strength. The closer it is towards that main charge, the stronger that electric field lines. The further away that charge is from the main positive charge, the weaker the electric field strength. Okay, so this is what it meant by electric field strength at any given point in the electric field is defined as the electric force acting on a unit positive charge placed at that point, which means that the closer, because remember I mentioned just now, this is supposed to be a positive charge. This is a main positive charge. Positive and positive are supposed to repel. They have repulsive force. So the closer it is towards the main charge, the stronger the repulsive force. The further away this sensor positive charge from the main rate charge, the weaker the electric field strength. So when it is a negative charge, all right, this is a negative charge. Electric field lines is moving towards the negative charge. So this is a positive test charge. All right. Again, because the definition uses a unit of positive charge. So this positive charge in a negative electric field, the closer it is towards the negative charge and positive charge are attractive force, right? They are opposite charges, so they will attract each other. So the closer it is towards the negative, the stronger the attractive force will be. The further away that positive test charge from the main one, the weaker the electric field strength. Okay, so this is what it meant by electric field strength. All right, from the definition, okay, this is the first formula that we're going to have in this chapter. E does not stand for energy here. E stands for electric field strength. So please do take note. When you see a Q at the bottom, all right, the E stands for electric field strength. So based on the definition, it's the electric force acting on a unit positive charge. So this electric field strength is equals to the electric force, okay, divided by a electric charge. And even though the definition here is positive charge, remember our charge in electricity can be a positive charge of atom with more protons compared to electrons. It can be negatively charged, whereby the number of electrons is more than the protons. All right, this Q, this symbol Q, can be positive charge or negative charge, even though the definition in textbook uses positive. Okay, so where am I? Okay, so the SI unit for electric field strength is Newton per coulomb. Because force unit is in Newton, charge unit is in coulomb. In a short while, I will explain regarding this electric charge. Okay, so up to here, are you guys okay? This is the first definition. The first formula for electric chapter. All right, the electric force over the charge is electric field strength. Okay. What happens if it's a uniform electric field? Okay, because previously when we draw, we have a positive charge with positive charge, negative charge with negative charge. We draw a circle because atom normally is in the circle. But what happens if that it is a uniform electric field? When it is a uniform electric field, the uniform electric field lines represents by a set of electric field lines. Mana laser represents by a set of electric field lines which are straight, parallel to each other, and equally spaced. So it has to be equally spaced. All right, that symbolizes uniform electric field. And this usually happens when it's produced by two flat parallel metal plates, which is charged, and one is positive, the other one is negative. And it is separated by a distance shown in the figure above. So the direction of the uniform electric field strength is from positive plate to negative plate. Again, we have drawn it just now. The electric field lines move from positive to negative. So can I ask, from this diagram, where is the positive plate? Top or bottom? Directly answer back at the chat box. Where is the positive plate? Top or bottom? All right, good. So majority of you actually mentioned bottom, which is good because it comes out from positive, enter negative. Okay. So that's the direction of electric field lines. Now, electric field strength, okay, right? This is for uniform electric field. Okay, I remember it's somewhere in your textbook. It's just a very small part. So electric field strength is produced by two parallel charge plates, right? Because just now, right, just now we have electric field is the force over the charge. Okay, this one is if we are talking about positive and negative charge itself of an atom. But if it's two parallel plates, we use the formula of the electric field is the potential difference between the two parallel plates. Normally, it's the potential difference of the power supply over the distance between the two parallel plates. Okay, so this is the second formula in electricity. Okay, the first formula is used for the electric field strength of a charge, all right, of a charge. This formula of electric field strength is for two parallel charge plates. So whereby the SI unit for electric field strength in this formula is volt per meter. Okay, so here, where is my simulation again? Okay, how do we manipulate this simulation, this particular formula? Okay, electric field strength is the potential difference over the distance between the two plates. Normally, when we have a power supply, okay, connected to a charge plate like this, okay, this is a positive, right? The longer line symbolizes positive, the shorter line symbolizes negative in the battery. So here, when it is positive, right, this plate will all be positively charged. All right, this plate will all be positively charged. And this one connected to the negative plate, this will all be negatively charged. Okay, so V, the potential difference, is normally the potential difference of the power supply. Okay, let's just say it's 12 volts. And then D is the distance between the two charge plates. This is D. Okay, so normally because the potential difference is supplied and it's constant, all right, this is a constant value. The electric field strength for this situation is inversely proportionate to the distance between the two parallel plates. Meaning means if these two parallel plates get closer towards each other, the D value decreases, the electric field strength will increase. Meaning means you will see more lines. All right, you will see more lines. Okay, but if the distance between them increase, the electric field strength will decrease. Meaning means you will see lesser lines, lesser electric field strength. Okay, so over here, all right, so we have a battery, 1.5 volts. Okay, I have two charge plate. When there's no battery, there's no charge. All right, so you need to make sure that you switch on the charge. So over here, even if I put it out like this, okay, there's no charge. Only when you connect it to a complete circuit, the one that is connected to the positive of the battery, it will be positively charged. The one that is connected to the negative of the battery, it will be negatively charged. Okay, so what happens here is the separation. We're going to focus on the distance. This is the distance separation between the two charge plate. Just now, we mentioned that as the distance increases, the electric field lines will decrease. So let's see whether does it really happen. So I'm going to pull this up. Notice the number of electric field lines has become lesser. But when I bring it closer together, the electric field lines, there's even more electric field lines. So which means that the electric field strength is also stronger. Okay, when you move further apart, less electric field lines, meaning means lesser electric field strength. So that is how the explanation for two parallel plates. And for your information, this concept is the concept behind capacitor. I'm not sure if you have learned this before in RBT. And it is also the same concept between battery, rechargeable batteries, and your power bank. All right, it uses this concept. Okay, So let's proceed. Harshini, I just saw your message. I'll reply you later on. Okay. So if two charge plate, okay, this is a little bit out of the current topic, because later on in the next few subtopic we will see this again. So I decided to put this in. Um, if a charged particle, right, I have two parallel plates, okay, one positively charged at the bottom, one negatively charged at the top. So there will be electric field lines moving from the positive plates towards the negative plate. If I were to have a electron, let's just say for example, an electron which is out of the surface of the metal placed in the electric field lines, okay, this charged particle, if held in between two plates and then I release, assuming that I can release this negatively charged atom, it will actually accelerate down towards positive. Reason why? Because it has attractive force. Another reason for this, okay, another reason for this is because this is negatively charged plate. It has, all right, the top is negatively charged. This is a negative electron plug. This is a negative atom. Against this negative plate, it will have repulsive force. Okay, and then with the positive plate, it will have attractive force. Okay, so what happens is when this charge is being released, it will actually accelerate downwards towards positive, because it wants to remember one thing. The main reason an electron move or a negative charge move towards positive is because negative charge has extra electron. Electronegativity wise, it is unstable. So it needs to share the electron. In order to share that electron, it needs to move and donate out that electrons towards charges which is lack of electrons, which are the positive charge. So that's the reason why normally electrons will move. Okay. So I hope up to here you guys are okay. Now, if the electrons, right, just now is I place polystyrene ball. Yes, it's the same concept, Daryl, because after this, we're going to discuss about the polystyrene ball and the flame. Now, if the electron is being shot perpendicular, means positive and negative charge plate, right? Electric field lines moving from positive towards the negative, that's the electric field lines. So if I take this electron and I shoot it perpendicular into this electric field lines, negative electron will be attracted towards the positive. Now, it won't directly go downwards. Why? Because it is being shot, which means it has energy. All right. It will, when it enters here, it will be attracted, but because the forward energy is stronger, it will keep moving forward first and then slowly be attracted by the negative, the positive plate. All right. There is a possibility that it will actually shoot here. If it not enough energy, it will hit the positive plate. It can only escape from this this charge plate if it has enough energy. This concept later on, we will talk about it, if I'm not wrong, in electronic. Okay, so I want you guys to have this concept. In electronic, you will see this picture again. Okay, so projectile motion means moving in a curved straight line now. Okay, now let's try this example. This is we have two formulas so far right now. Okay, we have two formulas so far right now. E equals to force, electric force over the charge Q. This is for the positive charges, positive and negative charges. But this question is two parallel plates. So if it's two parallel plates, it would be the electric field strength equals to the potential difference, which is the power supply, divided by the distance between them. Okay, so that's the two formulas. When my habit is when I learn the formula, I will keep on telling myself this is the first formula. What is it used for? When I get to the second formula, I will recall back what I have learned previous formula, write it out again, explain to myself what does all that symbol means, and then I'll write the second one and then explain what does it mean, where is it supposed to use for. So don't just memorize as E equals to F over Q. because E can also stand for energy. But when you see a Q meaning charge, this E is electric field strength. Okay, so the question says a positive charge object moves towards the right. A positive charge moves towards the right when placed between two parallel plates. Positive charge repels what? Positive charge repels what? Can you answer in the chat box? Positive charges repels. Positive charge repels negative. It repels positive. Positive, positive repel. Negative, negative repel. Positive attracts. Positive will attract what? Negative. So this positive is moving towards the right. So charge plate P is positive or negative? Plate P is positive or negative? Plate P would be positive. Plate Q would be negative. Good. Okay. So now the question says calculate the distance between two plates. We have the potential difference, 2000 volts. The electric field strength is 50,000 volt per meter. So using the formula of electric field strength equals to the potential difference over the distance. My habit, I put it as a subject first. Potential difference over electric field strength. So that would be 2000 divided by 50,000. So cancel, cancel, cancel. 225. So how much is this? 0.04 meter. Okay, so this is how you answer the question. Don't bother asking about the electric force formula. All right, there is electric force formula, but you do not need for SPM, so I'm not introducing it at all. Okay, so up to here, I hope you guys are okay. So this is the behavior of the charge that Daryl said. Are you guys okay? Do you want me to stop or do you want me to continue? Because it's almost like 9:30 already. So are you all okay if I continue a bit? Let at the very least the behavior of the charged particles. Are you okay? Can so whoever who cannot take it already, if you want to leave, then just go ahead lah, okay? So I'm just going to mention regarding the behavior of charged particles in the electric field. We have two situations. We have something missing in this picture. Okay. All right. Two situations that they ask in SPM. All right. We have a parallel plate. We put a ping pong ball in the middle. Another situation whereby we put a candle flame in the middle. Okay, so we're going to talk about a candle flame. Normally in school, I would show you guys this. So if you guys want to see this after we have settled quantum physics, we still have time after your trials. Ask me to take this out and show it to you guys. It's quite interesting to see. I rather you guys see it in school because after this, if you're not in physics anymore, you might not see it already. Cannot hear the sound now. Give me a quick minute.
So what am I looking at? Well, it's really, really simple. It's an electric field situation. So I've got a metal plate here, a metal plate here. I've got a negative connection on this one that's going to an EHT power supply, and a positive is the red.
So here's positive. Oh, sorry, not positive. This is negative here, here's positive.
One that's going to the other end of power supply. Now, I have a power supply that most schools do not have. It's 25,000 volts. So normally when people talk about EHT, they have like a 5,000 volt power supply. That works for a lot of stuff, but this is what you really need for the grown-up physics stuff. So it will not work with 5,000 volts. If you haven't got one, you'll just have to watch my video and enjoy it. You do need 25 kilovolts. Now, if I put a potential difference across here, there'll be a region of space where there is an electric field with field lines going across like so. And the field lines go in the direction that a positive test charge would move. So it's going from this plate to this plate because the positive is pushed this way. And the candle flame is there. This is going to show the electric field and what is happening to the ions. So when you burn things, when we combust, we have ions produced, and they're either positive because they have lost electrons, so it's a good thing to have less electrons, or they've gained it. Now, switching on my power supply, and
Watch the flame.
boom, straight away, 25,000 volts. I've got a major change in the flame. I'm going to dial it back down, and we've got a lovely shape again. So 0 volts. As I increase, flame gets shorter and fatter as ions are pulled in different directions. If I go right up again,
Notice
see,
that
point, it's slightly
the
more,
flame is moving towards the left direction,
more positive ions are
towards the
produced.
negative charge.
Actually, as I go further and further out, it's flattening more and more. Get an amazing little flicker. And there we go. That is showing the electric field going on this picture right to the left, the direction of positive charge would move, the test charge. If you have enough juice effectively in there, it will put the flame out. Now I'm going to try something simple. Very careful not to touch the electrodes. I'm going to move it slightly closer. See if we get, and there we go. Because the electric field between the plates is really strong, because E, electric field strength, is V divided by D. I put the candle out. There you go. Physics fun on a Tuesday.
So, okay, so hopefully with that video, it actually does substitute for the actual situation. All right, so this one is back in the textbook. Okay, the effects of the electric fields of a candle flame. Now, when I talk about the quantum physics in school, right, I told everyone saying that we all are made out of atoms. So all the materials are made out of atoms. So atom means they have nucleus, positive and positive protons and neutrons, and then we have the electrons orbiting outside. All of us has that. All the materials around us have that. So what happens here is that when, right, you can see all this over here. Now, what I want to mention is when we where's my light up? Okay, when the power supply is switched on, all right, the candle flame will spread out between the two metal plates. The spread of the flame will be towards the negative plates. Reason why? Because when we talk about atoms, all right, the positive charge is in the nucleus itself. All right, the most highest density of the atom is the nucleus itself, and flame, being a flame, it's heat, it is able to ionize the flame and to separate the positive and the negative charge. All right, that is where we ionize the flame, all right, whereby it causes it to separate very easily. Now, remember, because one thing, flame is heat energy. Heat energy, when electrons receive heat energy, it can easily move out and overcome the attractive force of the nucleus already. So when at the flame in an electric field charge, electric field strength, or the parallel plates, the heat from the candle flame causes the air ionize to form positive ions and negative ions. It actually splits out the protons and the electrons from its nucleus. So negative ions, all right, mainly are electrons, they will be attracted to the positive charge plate, while the positive ions, or the nucleus part, will be moved towards the negative charge plates. So positive ions have larger mass. If you were to recall back the mass of a proton, if I remember, is around 1.67 times 10 power of negative 27 kg. But electrons has 9.11 times 10 to the power of negative 31 kg. That's 10,000 times different. Okay, so 10,000 times different electrons are much more lighter compared to protons by 10,000 times. So therefore, the speed of the flame towards the negative charge plate is much more greater compared to the flame that is moving towards the positive plate, because the size and the mass is much more greater, 10,000 times greater for each of it. All right, so this is what happens of the candle flame in electric field. So next is the effect of electric field on a metal coated polystyrene ball. All right, if we were to be able to see this in the real life, it's really really interesting because you can just see the ping pong ball bouncing between the two metal plates. So I think I have a video later on, I'll play it. So what happens here is that when a polystyrene ball is displaced to touch the positive charge, this polystyrene ball, all right, you look at the power supply. The power supply here is connected to positive. So this line from the power supply, move your pen towards this plate and this plate will be positively charged. Okay, whatever terminal that is connected to the positive of the power supply, that is positive. The terminal that is connected to the negative power supply, that terminal is negative charge. Remember that, because when we carry out electricity experiment, you need to know how to connect the positive and the negative. All right, so when the polystyrene ball is pulled towards the positive charge and released, the polystyrene ball will swing to and fro between the two plates until the power supply is switched off. Okay, so let's see. Okay, I did get. All right, so very quickly, this is just a 1 minute video.
In this experiment, you will see a metal ball hanging on a string. The ball is electrically floating and is placed between two plates. 10 kilovolts is applied to one plate, while the opposite side is grounded. Under the intense electric field, the aluminum ball is attracted by the positive plate. Upon touching, it charges
So it
up
will
to
just keep
positive
bouncing to
polarity.
and fro.
Same charge repel, but opposites attract. So it swings towards the ground side, then repeats.
So only when you switch off the power supply, then it won't bounce
This
again.
is what happens when the electrons
Watch the plate. Again, what you saw just now was lightning. How lightning happens. Okay. Now answering Hans' question. Why does the fire of the candle extinguish when the metal plates are brought closer together? Because if you notice, when the flame is in between the two charge plates, it will flicker, all right, it will actually cause the flickering. So when it gets too close to each other, all right, where is my pointer? The formula is electric field strength equals to the potential difference over the distance. So when the distance get closer to each other, the electric field strength is very strong. So it is due to this electric field strength and later on connected to the electric force, that is the one that causes the flame to actually be extinguished. All right, it's something more further details. Okay, because the distance has been brought closer, the electric field strength becomes stronger. Okay, more detailed that one later on. Okay, Hans. So now over here, all right, this part in your textbook, or you printed out this PowerPoint slide, please make sure you put a remark over there. All right. They asked this question a few times already over the past few years. Okay, what happens to the ping pong, the polystyrene, the metal coated polystyrene ball, or the ping pong ball, right? When the power supply is on, but they didn't displace it. So in ideal situation, if the power supply is on, okay, where's my? When the power supply is on, the metal coated polystyrene ball, if it's placed in between, exactly in between, not slightly towards positive or slightly towards negative, exactly in between of the two distance, the polystyrene ball will not move. All right, because the polystyrene ball, even though it is coated with metal, it is neutrally charged. Neutrally charged doesn't mean there's no positive or negative. All right, it means that the number of protons and the number of electrons is the same in the atom. The positive charge and the negative charge atom has the same value. It's neutral. Okay, so what happens when you take the polystyrene ball, we move it closer towards one of the plate. So when we move it closer towards the one of the plate, for example here, it moves closer towards the negatively charged metal plate. So when it moves closer to the negative charged metal plate, the positive charges will discharge. All right, how does it discharge? Either the electrons will go to the positive charge, and because it's negative charge plate so the negative from this plate will move into the ping pong ball also, or the polystyrene ball, causing this polystyrene ball to be heavily negative charge, as what is standard written here. I repeat, when the polystyrene ball neutral displays towards the negative, the positive charges on the ping pong ball, because previously it was ping pong ball, the polystyrene ball, all right, it will get neutralized by the negative charges on the negative terminal. And then because it's still connected, so the negative will move into the ball and causing this ball to be negatively charged. It's connected to the negative terminal. So when negative ball with a negative plate, it will have repulsive force. And then with a positive, it has attractive force. So it will swing towards the positive due to the attractive force. Okay, so this is what it meant over here. The negatively charged polystyrene ball will be attracted towards the positive plate, metal plate, because it's attractive force. Then when it reaches the positive plate, it's negatively charged. So the electrons from the ball will be transferred towards the metal plate because it's positively charged. It get neutral, but more electrons will go in still. All right, those that is atoms inside here, because this is strong positively charged, extremely high tension, 20,000 volts to 25,000 volts, very high tension. So it will actually cause the other atoms inside here, the electrons, to move towards the positive plate as well. So when it moves towards the positive plates, number of electron becomes less than the proton, or the number of the negative is lesser compared to positive. This will cause the ball to be positively charged. When it's positively charged, nearer to the positive plate, it will repel and it will be attracted towards the negative charge plate. So then the positive ball will be attracted back to the negative charge plate. So that's the reason why that video just now, it keeps on repeating, moving left and right, left and right, left and right, until when it will continue until the power supply is switched off. All right, so that was what the whole entire video was explaining about. Okay, so are you all okay with this explanation? Any other questions you want to ask me? Okay. Okay. I can't continue any further because my girls need to fall asleep already. Okay, so I'm gonna stop the class today. If you have any questions, please do ask me.